Hello everyone. So in continuation of our earlier discussion on statistical inferences, today again we'll be learning few more topics on that. Today what we will see is statistical inferences on the proportion of success in a binomial population. So we have seen statistical inferences on mean. Okay, we have also seen how to find out the confidence interval as well. So now we'll be seeing statistical inferences on the proportion of success. And when we talk of proportion, I think you guys can remember. So when we want to infer something about the proportion of a population, the populations, then we could find out that it has the characteristics of a binomial population. The random variable, basically it has the characteristics of a binomial distribution, and that's why we can consider the population as a binomial population. And moreover, the sampling distribution also, for the sampling distribution of the proportion, we have seen that we can use normal distribution if the sample size is larger. Okay, so that as I told you again and again, sampling distribution is basically the backbone of any inferences. So when we will be seeing the proportion of statistical inferences on the proportion of success, we will actually consider the sampling distribution of the proportion. Similarly, we will also see statistical inferences on the variance of a normally distributed population. When we have to infer about the variance, rather I should say when we use chi-square distribution or t distribution, always our population has to be a normal population, if not normal, at least not too much away from a normal population. Otherwise the data that we will get, it will not be a precise result. So that chi-square distribution, F distribution and t distribution is very much sensitive to normality assumptions that we have seen again and again. Okay, so now first inference on a proportion, we will start with an example. So this example is a good way to understand that concept, isn't it? So like what in this example, what we have here, an advertisement claims more than 60% of doctors prefer a particular brand of painkiller. More than 60%, that is basically it is talking about the population. See, it is talking about the whole population as a whole, about the whole lot. It is talking that more than 60% of the doctors prefer a particular brand. That means I can say p is equals to, small p is equals to 0.6. That this is the quotient. An agency established to monitor truth. An agency, advertisement is claiming that more than 60% of the doctors prefer this particular brand. An agency, a third party, basically a third party, to monitor the truth in advertising, conducts a survey consisting of a random sample of 120 doctors. So, and a third party basically wants to see whether it is really correct. So, what it does is that it takes a random sample of 120 doctors. So, out of 120 questions, 82 indicated a preference for the particular brand. Okay, so what is my proportion? Is 82 by 120, isn't it? My p cap is 82 by 120. Proportion of the sample which has preferred that particular brand. So, is the advertisement justified? Now, the question is, with this proportion, when assuming that, because advertisement is claiming that this is true, advertisement is claiming that p is equals to 0.6, and from the sample what result I got, this proportion of the sample which actually prefers this brand is 82 by 100. So, this is, of course, this is correct because this we have tested it. Okay, this is not something which we have tested it. This is we have tested it. So, assuming this correct, is this is possible? That's what we will check, right? So, is the advertisement justified? So, if we get a quite acceptable probability for this, then we can say yes, acceptance, advertisement is justified. Here actually I want to bring to your notice is that first, definitely it's a question of hypothesis testing. We'll do hypothesis testing. Now, how to frame the hypothesis? See here, if we frame, now here who is doing the research? A third party. So, when the third party is conducting the research, what the third party wants to prove? As I told you, the alternate hypothesis is always something what you wants to prove. So, the third party wants to prove whether it is greater. Okay, it has doubt in the advertising, so it wants to prove that whether it is greater. So, definitely alternate hypothesis is p greater than 0.6. And Null hypothesis is p is equals to 0.6. Okay. Why I am discussing this question? Because I want to bring to your notice one more thing. Suppose this same example, the same thing, if instead of the third party, even if the the particular manufacturer, who have advertised, if the manufacturer wants to do this experiment, wants to check, then how he would have formed the hypothesis? Okay, because the manufacturer, he believes that 60% of the doctor prefers this brand. He believes that. Okay, so for him that is the status quo, that it is greater than 0.6. Okay, so he wants to check whether it is less than. He doesn't want that less than to happen. He wants, because type 1 is something which we want, null hypothesis is something which we want that to happen. That's why we have kept type 1 error very less amount. Usually type 1 error, the significance level, that is the significance level is a very less value we keep, isn't it? Because we always put that in null hypothesis which we want it to happen, because it maintains the status quo. So if the particular manufacturers wanted to test this, then for them they would have framed a hypothesis. They wouldn't have framed this hypothesis. Instead, what they would have framed the hypothesis, their alternate hypothesis will be p less than 0.6. They would have want to prove, is it p less than 0.6? They just for checking purpose. They are sure that it is greater. So for them that it is greater, that means greater or equal. So as I told you, null hypothesis we always specify with equality. So if it is less, because again one more thing I have mentioned, remember, both the hypotheses are exhaustive, isn't it? It should cover all the things. So if it is less, then definitely it will be, other one will be greater and equal, so as to cover all the things, all the values. So if the manufacturing firm would have framed a hypothesis, they would have framed in this way, but now it's a third party. They want to prove whether it is really greater than 0.6, so they are framing the hypothesis as p greater than 0.6. Okay, so fine, we have this. Now how to test it? It's given a significance level of 5%. So it is a one tail. So when it is a one tail, we'll have only one rejection region. So for greater than, it is in the greater than 0.6, that means our rejection region will be in the upper tail. When we are talking of this is the normal distribution, this is the upper tail, this portion is the upper tail, this portion is the lower tail. So when we are looking for whether it is greater, so our rejection region will be in the upper tail, because our null hypothesis is less than equals to, isn't it? If it is greater, what is our null hypothesis? Null hypothesis is basically less than equals to. So if we get a value which is much greater, that means in the upper tail, then we can say that the null hypothesis is rejected. So this is the case, p greater than 0.6. So it is given significance level of 5%. So we have to find out the rejection region in this region, in the upper tail. Okay, so how we will definitely will be using the Z statistics here. That is the Z distribution. What is the value for this? It is p bar, p cap minus p. So it is p cap minus p. Then it is the sigma by root n. What is the standard deviation from the binomial population? It is, we got a p into 1 minus p, right? So this is p into 1 minus p. We have done it while discussing sampling distribution. Here the standard deviation is p into 1 minus p, that is, so this is p 1 minus p by 120, so we got 1.86 value. So corresponding to 1.86, there's two ways of doing it. Either you find corresponding to this 5% significance, what is the critical region that you find. If the value what we get from the Z, if this value is greater than the critical region value, then we reject the hypothesis. Another way is that we find the p value of this. And critical significance level is given 5%. That means our 5% means it is 0.05. Area is 0.05. So if it's the area corresponding to this is lesser than 0.05, then we will reject the hypothesis. So let's do it by computing p value. You can do the other one, whatever way is there. So p value for this is, you'll get it from the table. It is one tail, so you don't have to plus it twice. So it is 0.03, and 0.03 is less than 0.05. So if this portion is 0.05. So 0.03 will be somewhere say this portion. So it falls in the critical region, so therefore reject H0. Now this is using hypothesis testing. We have also learned the other one approach, that is the confidence interval estimation. Okay, so confidence interval estimation I have already discussed under what situation we use. The two situations. First, number one is that when we don't have any hypothesized value, we cannot guess, we cannot make a guess what will be the hypothesized value. In that case, we just have to estimate. How we estimate? We take a sample. From the sample, we calculate the particular statistics, whichever we are interested, and based on that statistics we call it as a point estimate. Based on the statistics, we form the sampling distribution of that statistics, and then we find out the confidence interval. Excuse me, that is one way. Another way is that, not another way, that is the one reason why we go for confidence interval. Another reason is that supposing the hypothesis is rejected. So like we have done an example, mu is equals to 8. Alternate hypothesis is mu not equals to 8. So if mu equals to 8 is rejected, that means mu is not equals to 8. Now mu not equals to 8 means what is the value of mu? So in that case also we can find a confidence interval to know actually mu falls in what range. Okay, so now similarly for proportion also we can find a confidence interval. So same whatever formula we use to find out the confidence interval for inferences and mean, same formula for to find out the confidence interval estimation for a mean. What was the formula? If you remember, it was x bar plus minus z alpha by 2 sigma by root n, isn't it? X bar plus minus z alpha by 2 sigma by root n. So here instead of x bar is the mean of the sample, so we have proportion, that is p cap. Okay, and we have sigma. What is this sigma? This thing's place in see. Notice what is sigma is the population standard deviation. Remember, sigma is the population standard deviation. So, and when we use when the population standard deviation is not known to us, then we use t distribution. In case of t distribution, instead of sigma we had s, isn't it? S, that is the standard deviation of the sample. Right? Here similarly, here when we consider the standard deviation, so what is the standard deviation of the population? Standard deviation of the population is equals to p into 1 minus p. But if we don't know the hypothesized value, what is the p of the populations, then what we will use? Like for t distribution we use S. Similarly here, if the p is not known to us, the sample proportion p cap is substituted for p in the formula for the variance. Okay, we substitute p cap. When we when we calculate the estimation, it is mostly because we don't have the value of p. We don't have the proportion value and proportion of the population. So we substitute p with p cap. So my standard deviation is p cap into 1 minus p cap. So you see this example here. A pre-election poll using a random sample of 150 voters indicated that 84 favored candidates meet. So that means my p cap. This is my p cap. It is not talking about the whole population. It has taken a random sample of 150. So what is my p cap? P cap is 84 by 150. Construct a 0.99 confidence interval. We have to construct a 0.99 confidence interval. If the 0.99 confidence interval, what is the significance level? That means alpha is 0.01. Okay, alpha is 0.01. So if it is a two-tail, if you have to check for two-tail, 0.01 means it will be both sides is alpha will be equals to 0.005. Isn't it? If it is two-tail, but if it is single-tail, we will just consider alpha is equals to 0.01. Okay. Now see, this question is for two-tail or single-tail, whatever what it is asking. Construct a 0.99 confidence interval on the true proportion of the voters favoring Smith. Okay. So it is not talking about any single population, one tail or two tail. It is not talking about anything, and we don't know the value of p as well. We just whatever information we have just from the sample, like the example what I have given. So a person wants to open a retail outlet and he doesn't know the spending capacity of the people. So he has just taken a sample and tried to find out what is the annual income of the people. So he doesn't have any idea, so he just took out the value from the sample. So similarly, we just have the sample value. We don't have any idea what may be the population proportion. We don't know P. So P, we found out P cap here. So comment on whether Smith can predict with 0.99 confidence that she will win the election. Okay. So now here we have P cap is this, alpha is equal to 0.01. Okay. So now what is the confidence interval here? The confidence interval, same value, whatever we used here. This is the confidence interval, P cap plus minus Z alpha by 2, P cap into 1 minus P cap by N root over. So just putting the value, this is Z of alpha by 2, value corresponding to that is 2.576. You can see it from the Z table. So we got, this is the value we got. This is the confidence interval from 0.45 to 0.66. That means, what is the last question it is asking? Comment on whether Smith can predict with 0.99 confidence that she can win the election. For winning the election, at least more than 50% should vote, right? So here the person who are voting is, we have values below 0.5 also. Of course, we have values above 0.5, but we have values below 0.5 as well. So since the interval contains values below 50% also, this implies Smith cannot predict with 0.99 confidence that she will win the election. Fine. So now next is, we will see how we infer on the variance of one population. All this we are considering for one population. Okay. So variance for one population, similarly the way we do it for mean, we have done it for proportion. Similarly, this will be our null hypothesis, this is our alternate hypothesis. Then, and for proportion, I mean for variance, what is the statistics we use? Remember, for to find out the sampling distribution of a variance, we have used the statistics n minus 1 s square by sigma square. This is the value, and this n minus 1 s square by sigma square, it has a chi-square distribution. Remember, we have seen it has a chi-square distribution with degrees of freedom n minus 1, isn't it? So this has a chi-square distribution. And what is this n minus 1 s square? You can also tell is a sum of SS. It is called sum of squares basically. I have shown you why it is called sum of square, because if you find out the formula for s square, what you get? Remember the formula for variance. The whole portion is basically, and then it is 1 by n minus 1 summation of xi minus x bar whole square. This is the formula for s square. So if I bring n minus 1 here, n minus 1 s square, what remains is this summation of xi minus x bar whole square. So this is a summation of square. That's why n minus 1 s square is also called summation of squares. So there is nothing so great about that. So you can use either this or you can use this. So basically n minus 1 s square by sigma square, it should, the statistics chi-square, if the null hypothesis is true, this statistics n minus 1 by s square by sigma square, this statistics has chi-square distribution with n minus 1 degrees of freedom. Okay, that we have already seen. So now we'll have to find out, for if we want to infer on the variance, we'll have to find out the value of this statistics, and then we'll have to see whether this has a chi-square distribution. Basically, meaning it has a chi-square distribution means it has to have a significant probability. Okay, not if it has very less probability. We have seen it is 95% of the value falls within what range? If you remember, I have discussed that. So if it is so chi-square distribution. Chi-square distribution, we have something of this sort. So 95% of the value basically satisfies this, satisfies the chi-square distribution of the for the hypothesized sigma value. If our value falls in this region, why will our value falls in this region? If we assume the variance to be very, very small, which is very unlikely, very, very small. Of course, it can happen. It is not that it is, but it is very, very unlikely. If we assume a variance to be very small, we will get in this range. Again, if we assume a variance to be very big, very high, then it will fall in this range. That is also quite unlikely. A very high variance is a very unstable process. So that is also quite unlikely. So if our value falls within this 95% range, then we can say that it satisfies the chi-square distribution. So now here, So what is the rejection region? Corresponding to a particular significance level. So remember how to find out a rejection region. So it is like, let me write it here only. So it is n minus 1 s square by sigma square. Basically from the confidence interval, it will be easier to write it this way: chi square 1 minus alpha by 2. This is less than equals to chi square alpha by 2. This probability is equals to 1 minus alpha, isn't it? My this value n minus 1 s square by sigma square, it should fall between this chi square alpha by 2 or chi square 1 minus alpha by 2. Okay. So that means what is my rejection region? If my this statistics, if it is greater than chi square alpha by 2, greater than chi square alpha by 2 means this region, then we reject it. Or this value, if it is less than this value, chi square 1 minus alpha by 2 is value, chi square alpha by 2 is this portion. So if it falls in this region or this region, then we reject the hypothesis. So reject A0 if this is true or if this is true. Okay. Coming back. So now if you see here, hypothesis tests on variance are often one tail, because variability is a measure of consistency. Hypothesis testing, when we try to find out, infer on the variance, usually when we try to infer on the variance, we never try to infer on the, if a variance is smaller than this value, because we need smaller variance. What does smaller variance indicate? Smaller variance indicate consistency. So if any product, any equipment, any material, whatever it is, we want variance to be as less as possible. Okay, so smaller variance is a positive thing for us. So definitely we will not try to check for, usually we don't try to check for a smaller variance. What we try to check for, whether it is greater variable. Okay, so mostly in hypothesis testing for inference and variance, it is usually that means we test for high greater variances. That way it is single tail. Say alternative hypothesis of a larger variance implies an unstable or inconsistent process. So in unstable process, no point carrying out a hypothesis testing or confidence interval estimation. So now what is the confidence interval? We have seen the using hypothesis testing how we do this. Now we will see how the confidence interval for variance. So this is what just now what I have mentioned. If the confidence coefficient is 1 minus alpha, if the significance level is alpha, my confidence coefficient is 1 minus alpha, right? If it is 5, confidence coefficient is 95%. So probability that it falls within this range is 1 minus alpha. That my this statistics falls is less than the chi square alpha by 2 and greater than chi square 1 minus alpha by 2. Okay. So if I simplify a bit this whole thing, if I simplify a bit, how I have simplified, just divided both sides by n minus 1 s square. Just simple simplification, I will get this value. Okay, so my sigma square should fall within this range. What range? N minus 1 s square by chi square alpha by 2, n minus 1 s square by chi square 1 minus alpha by 2. Okay, so this is the confidence interval. Confidence interval for confidence coefficient 1 minus alpha. So the lower interval, lower limit, which is the lower limit is n minus 1 s square by chi square alpha by 2, or I can tell ss by chi square alpha by 2. This is my lower limit. What is my upper limit? Is ss by chi square 1 minus alpha by 2. Okay, this is my upper limit. So we will see a problem for that. In processing grain in the beverage industry, the percentage extract recovered is measured. A particular beverage industry introduced a new source of grain, and the percentage extract on 11 separate days is as follows. This is a sample what we have taken. Regarding the sample as a random sample from a normal population, variance, of course the population has to be normal, calculate a 90% confidence interval for the population variance. We have to calculate the 90% confidence interval. Here we don't know what is the population, the variance is not given. We don't know what may be the population variance or population standard deviation. We just have taken a sample. From the sample we got this data, and from this data we will calculate the 90% confidence interval. So basically from this sample we will try to find out the value of S square. Once we find out the value of S square, that is the variance from this sample, then n minus 1, that is here total 11 days, so n minus 1 is 10, n minus 1 S square by sigma square. Okay, so this is the what to say, this is the statistics we have to find out. Okay, so what happens? So what does the confidence interval say? See here, this, to find out this, I don't have the value of sigma square. I don't know what is the value of sigma square here. I know only S square. So I cannot use sampling distribution based, I cannot hypothesize the value because I don't have any idea. So definitely I cannot use hypothesis testing here. What I will do, I will just go and find out the confidence interval. To find out the confidence interval, what was this? This is the formula. Remember, this is the upper limit, lower limit, this is the upper limit. Okay, so I found out X bar, I found out S. Then what is the chi square alpha by 2? Chi square alpha by 2 is this value, that will find it from the chi square table. What is alpha? Alpha is given is 10%. So alpha by 2 will be 5%, that means 0.05. What is chi square value corresponding to 0.05? With 11, it is 10 degrees of freedom. With 10 degrees of freedom, we'll get it from the chi square table. And similarly for this is 1 minus alpha by 2, chi square of 1 minus alpha by 2 for 10 degrees of freedom, we'll get this value. So now once we know this value, we can find out the interval, lower interval and upper interval and lower interval using the formula. Okay. So that's all in this class. So what we have learned the estimation of confidence interval for population proportion and population variance. Okay. So I have tried to illustrate the concept with some examples, and in the next lecture we will cover a quick tutorial before starting the discussion on the inferences for two populations. So these are the reference. Thank you guys. Thank you.